In question number 16, moment of inertia is decreased by 36%. So new moment of inertia will be 0.64 of initial moment of inertia. We want to find the percentage change in radius of gyration. Now we know that I is directly proportional to r square as mass remains constant. So I2 by I1 is equals to r2 square divided by r1 square. From this we can write I2 by I1 is equals to 0.64 is equals to r2 square by r1 square. So r2 by r1 whole square is equals to 8 by 10 whole square. So r2 by r1 is equals to 0.8. So new radius of gyration is 0.8 times original radius of gyration. So percentage change can be found as r2 minus r1 upon r1. That's it, 0.8 minus 1 r1 upon r1 into 100%, that is 20%. It is negative, so it is decreasing by 20%. So radius of gyration is decreased by 20%. So option 3 is correct option. In question number 17, a diatomic molecule is formed by connecting two atoms of mass m1 and m2 with a light rod or string of distance or length r. We want to find the moment of inertia of the system about an axis passing through the center of mass and perpendicular to this string. For that, first we have to find the position of center of mass. Let's see, we are taking this position as origin. The distance of center of mass is x cm and distance of m2 will be r. So x cm will be m1 x1 plus m2 x2 upon m1 plus m2. So x cm, here x1 is 0 as m1 is located at origin. So 0 plus m2r divided by m1 plus m2. So position of center of mass from m1 is m2r divided by m1 plus m2. We can redraw this diagram. M1, this distance is m2r upon m1 plus m2. This is m2. So this distance will be r minus m2r upon m1 plus m2. Simplifying this, let's say this distance is x. So x is equals to m1r upon m1 plus m2. Now we have found the position of center of mass and distance of m1 and m2 from center of mass. To write the moment of inertia, I is equals to I1 plus I2. I1 is the moment of inertia of m1 and I2 is the moment of inertia of m2. m1 r1 square, distance of m1 from center of mass is m2r upon m1 plus m2 whole square plus m2, and distance of axis of rotation from m2 is m1r upon m1 plus m2 whole square. Taking m1, m2 and r square common, in the bracket the denominator m1 plus m2 whole square is also common. Here m2 plus here m1. So I is equals to m1 m2 r square divided by m1 plus m2. So option 3 is correct option. In question number 18, a wheel is initially stationary, so omega naught is equals to 0. It starts rotating about its own axis with uniform angular acceleration, that is alpha is equals to 8 radian per second square. We want to find the time taken by it to complete the 77 rotations. Now angular displacement for one rotation is 2 pi. So for 77 rotation, it will be 77 into 2 pi. Simplified, pi is 22 by 7 into 77. So theta, angular displacement, will be 22 into 22. Now with the analogy, we can use the equation theta is equals to omega naught t plus half alpha t square. Here initially the wheel was at rest, so omega naught is 0. Theta is given, that is 22 into 22. Half alpha is given as 8 into t square. Simplify this, we'll get t is equals to 11 seconds. So option 3 is correct option. In question number 19, it is given that a ballet dancer initially is rotating with angular velocity omega. Now the ballet dancer folds his body close to his axis of rotation, by which radius of gyration decreases by 1 by 4. Let's say initial radius of gyration was r1. Now he decreases its radius of gyration by 1 by 4. So new radius of gyration will be r1 minus r1 by 4. So r2 will be 3r1 by 4. Now there is no external torque acting on the person, so angular momentum will be constant. So we'll use conservation of angular momentum here. So initial angular momentum I1 omega 1 is equals to final angular momentum I2 omega 2. Initial moment of inertia we can write as m r1 square into omega. Final angular momentum is m r2 square into omega 2. M will get cancelled out. So omega 2 will be r1 by r2 whole square into omega. From this equation we can write r1 by r2 is equals to 4 by 3. Put this value in this equation. Omega 2 is equals to 16 by 9 omega. So option 4 is correct option. In question number 20, it is said if the earth shrinks such that density becomes 8 times the present value, so new density d2 will be 8 times the original density d1. We want to find the new duration of the day in hours. Here consider that mass will remain constant. No external torque is acting on the system, so we'll use conservation of angular momentum. So I1 omega 1 is equals to I2 omega 2. Earth is solid sphere, so moment of inertia will be 2 by 5 m r1 square omega 1 is equals to 2 by 5 m r2 square omega 2. This 2 by 5m will get cancelled out. So r1 square omega 1 is equals to r2 square omega 2. We want to find the time duration. So we'll replace this omega with 2 pi by t. So r1 square into 2 pi by t1 is equals to r2 square into 2 pi by t2. r1 square by t1 is equals to r2 square by t2. So T2 by T1 is equals to R2 square by R1 square. Now we want to find the ratio of radius so that we can find the new time period of revolution. For that, the relation between density is given. Here mass will remain constant. Mass is equals to density into volume. So d1 v1 is equals to d2 v2. So v1 by v2 is equals to d2 by d1. Volume ratio is the ratio of cube of radiuses. So r1 by r2 whole cube is equals to d2 by d1, that is 8. So r1 by r2 is equals to 2. Put this value in this equation. So T2 by T1 is equals to 1 by 4. We want to find the new time period of revolution. Present time period of revolution is approx 24 hours. So 24 divided by 4, so 6 hours. So option 3 is correct option. Question number 21. Initially a disk of mass m and radius r was rotating about its axis with angular velocity omega 1, that is equal to omega. Now another disk of same mass but half radius is placed on it. We want to find the combined angular velocity of this system. Here external torque is 0, so again we will use the concept of conservation of angular momentum. So initial angular momentum is equals to I1 omega 1 and final angular momentum is equals to I2 omega 2. Initially only one disk is in this system, so moment of inertia will be mr square by 2. Omega 1 is omega is equals to. Finally there are two disks in this system, so total moment of inertia will be addition of individual moment of inertia of the disk. Moment of inertia of this disk will be mr square by 2 plus moment of inertia of this disk will be m. Its radius is r by 2 whole square divided by 2 and their combined angular velocity is omega 2. Mr square by 2 omega is equals to mr square by 2 plus mr square by 8 into omega 2. By simplifying this we can get omega 2 is equals to 4 by 5 omega. So option 2 is correct option. In question number 22, two bodies are given, one having moment of inertia 3 kg meter square and angular velocity omega 3 radian per second. Another body is having mass 27 kg. They both are having same kinetic energy. This body is rotating, so it will have rotational kinetic energy, and this body is moving linearly, so it will have linear kinetic energy. We want to find the linear velocity of this body, so simply we will combine the kinetic energy of both the bodies. Rotational kinetic energy is half I omega square and linear kinetic energy is half m v square. Put these values, this half will get cancelled out. I is 3 into omega square, that is 9. Mass is given 27 kg into v square. So v square will be 1. V is equals to 1 meter per second. So option 1 is correct option. In question number 23, a circular disk of mass m and radius r is rotating about its axis. An external force F is applied along its edge. So this force will create torque. The angular velocity of disk is increased from 0 to omega. So initial angular velocity is 0 and final is omega. We want to find the work done by this force during this time t. Now work done is equals to force into displacement for linear motion. From the analogy we can write work done is equals to torque into angular displacement theta. Here torque is r cross f, so torque is rf. Now we want to find the angular displacement theta. For that we can use this equation. Theta is equals to omega naught t plus half alpha t square. Omega naught is 0, so theta is equals to half alpha t square. Now we have to find the angular acceleration alpha. For that we know initial and final angular velocities, so we can use this equation. Omega is equals to omega naught plus alpha t, omega naught is 0, so omega is equals to alpha t, so alpha is equals to omega by t. Put this value in this equation, so theta will be half into omega t. Your work done will be torque is R into F into theta, theta is omega t by 2. So this is the work done by the force F. So option 3 is correct option. In question number 24, we want to find the work done by tangential force F. During the displacement of theta. We know work done is torque into angular displacement theta, and torque is R cross F, so work done will be RF theta. Option 1 is correct option. A flywheel having moment of inertia 0.2 kg square. It was initially at rest, so omega naught is 0. A constant external torque of 5 Newton meter is applied on a wheel. We want to find the work done in next 10 seconds. So t is equals to 10 seconds. Here we can use work energy theorem. According to work energy theorem, work done is equals to change in kinetic energy. Here object is rotating, so we'll use rotational kinetic energy. So work done is equals to final kinetic energy minus initial kinetic energy. Initially flywheel was at rest, so initial kinetic energy will be 0. So work done will be equal to half I omega square. We know moment of inertia of flywheel, so now we have to find the final velocity of flywheel after 10 seconds. We can use this formula, omega is equals to omega naught plus alpha t. Omega naught is 0. Now we know tau is equals to I alpha, so alpha will be tau divided by I. So tau divided by I into t. Torque is given as 5. Moment of inertia is 0.2 into time is 10 seconds. So omega is equals to 250 radian per second. Put this value in this equation. So work done is equals to half. Moment of inertia is 0.2 into 250 square. Solving this, we'll get work done is equals to 6250 joule. So option 4 is correct option. In question number 26, 3 particles each of mass 1 kg are placed at the corners of a right angle triangle OAB. The mass of each particle is 1 kg. Here O is taken as origin, OA as positive x-axis and OB as positive y-axis. It is given that OA and OB is 1 meter. We want to find the position vector of center of mass. This is two-dimensional system, so we'll use XCM is equals to M1x1 plus M2x2 plus M3x3 upon total mass, that is 3 kg, and YCM is equals to M1y1 plus M2y2 plus M3y3 upon total mass, that is 3. For simplicity, we'll write the coordinates of each mass particle. This is origin, so its coordinates will be 0, 0. A is on x-axis, so its coordinate will be 1, 0, and B is on y-axis, so its coordinate will be 0, 1. Put this value in this equation. XCM will be, for this coordinate is 0, 1 plus this also 0, 0 plus 0 divided by total mass 3. For YCM, this component will be 0, this component will be 0, for this 1 divided by 3. So position vector of center of mass will be I plus G divided by 3. So option 1 is correct option. In question number 27, it is given that a bomb of mass m was initially at rest and it was at origin. Now it is exploded into 3 equal pieces, m by 3, m by 3 and m by 3. One piece is located on x-axis at x is equals to 40 centimeter. The other piece is located in xy plane at x is equals to 20 centimeter and y is equals to minus 60 centimeter. We want to find the position of this third particle. Here note that the explosion force is the internal force of the system. As there is no external forces acting on the system, the velocity of center of mass will be 0. So center of mass will be located at origin only, even after explosion. So xcm will be 0 and ycm will also be 0. We'll write the equation for xcm, that is m1x1 plus m2x2 plus m3x3 upon total mass. m1 is m by 3 into its position vector 40 plus m2, that is also m by 3 into its position vector, that is 20, plus third m by 3, let's say its position is x, divided by total mass m, and this xcm is 0. By simplifying this, we'll get x is equals to minus 60 centimeter. Same way, writing for y-axis, ycm is also 0. So 0 is equals to m1 by 1. Its y coordinate is 0. So 0 plus its y coordinate is minus 60 plus this mass is m by 3. Let's say its y coordinate is y divided by total mass m. By simplifying this, we'll get y is equals to plus 60 centimeter. So coordinate of third particle will be minus 60 centimeter along x-axis and plus 60 centimeter along y-axis. So option 3 is correct option. In question number 28, it is given that n mass particles of mass m, 2m, 3m, 4m up to nm respectively are placed from a fixed point at a distance of L, 2L, 3L up to NL respectively. We want to find the position of center of mass from this fixed point. Let us take this fixed point as an origin. So xcm is equals to m1x1 plus m2x2 up to mnxn upon total mass, that is m1 plus m2 plus mn. Here mass of first particle is m and its length is L, plus mass of second particle is 2m and its length is 2L. Mass of nth particle will be mn and its distance will be nl. Divide by total mass m plus 2m plus 3m up to nm. Taking m and l common from numerator, in bracket 1 plus 2 into 2 4, next 3 into 3 9, next 4 into 4 16 up to n into n square, divided by taking m common 1 plus 2 plus 3 up to n. Here m and m will get cancelled out. Now this is the square series, 1 square plus 2 square plus 3 square up to n square is equals to n into n plus 1 into 2n plus 1 divided by 6. And for this, 1 plus 2 plus 3 up to n is equals to n into n plus 1 divided by 2. Put these values in this equation, we'll get xcm is equals to 2n plus 1l divided by 3. option 1 is correct option. In question number 29, it is given that initially 4 identical mass particles, each of mass m, are placed at the corners of square of side L. Now one of the mass is doubled, so the center of mass will get shifted. In this case, center of mass was at the geometric center and it was having distance of L by root 2 from each corner. We want to find the shift in the center of mass, in this case from the opposite point. From this point we have to find the shift. Now in this case, at this point, initial extra m mass is added to the system, so shift can be written as m L by root 2 divided by, now total mass will become 5m instead of 4m. So shift will be, this m will get cancelled out, L divided by 5 root 2. So option 4 is correct option. In question number 30, a disk is given. Let us assume its mass is m, its radius is given as r. Now a small disk of radius r1 is cut and center of this small disk is placed at a distance from O. We want to find the new center of mass of remaining disk. This is the remaining portion. We want to find the center of mass. Now center of mass always lies towards the larger mass, so center of mass will be shifted in this direction. Let's say it is at the distance x from O. This is our new center of mass. If this distance is taken as positive a, then this will be negative x. We want to find this minus x. In question number 30, a disk is given. Let us assume its mass is m, its radius is given as r. Now a small disk of radius r1 is cut and center of this small disk is placed at a distance from O. We want to find the new center of mass of remaining disk. This is the remaining portion. We want to find the center of mass. Now center of mass always lies towards the larger mass, so center of mass will be shifted in this direction. Let's say it is at the distance x from O. This is our new center of mass. If this distance is taken as positive a, then this will be negative x. We want to find this minus x. We can consider this to be a system of two particles. Its mass is m1 and the mass of remaining portion is m2. If we combine them, again center of mass will be at O. Take O as origin, so center of mass of whole system lies at O. Now first we have to know the mass of this cut portion and mass of this remaining portion. For that we will use the concept of density. Here density of all three portions are same, so density is equals to constant. So we can write mass upon volume is equals to constant. Mass is directly proportional to volume. Here for disk, mass is written as area into thickness. Thickness of cut portion and remaining portion both are same, so we can write mass is directly proportional to area. This is called area concept. Now mass of whole disk is taken as capital M and mass of cut disk is taken as small m. Area of whole disk is pi r square and area of cut disk will be pi r1 square. So the area of remaining portion will be total area minus cut part pi r1 square. So this will be pi r square minus r1 square. Now let's say mass of this cut portion is m1 and mass of this remaining portion is m2. If we consider the combination of these two objects, the center of mass of this system will be at origin. That means its x coordinate will be 0. So we can write the equation xcm is equals to m1 x1 plus m2 x2 upon m1 plus m2, and here xcm is 0. So we can write m1 x1 is equals to minus m2 x2. Here m1 is the mass of cut portion, x1 is its distance from origin, that is E, is equals to minus m2 is the mass of remaining portion into x2 is the distance of center of mass of remaining portion. We have assumed it to be x, but it is in negative direction, so take it as minus x. So m1e is equals to m2x. So x will be a m1 upon m2. From this we can write mass ratio as ratio of area. m1 is pi r1 square and m2 is the pi r square minus r1 square. So x is equals to a r1 square upon r square minus r1 square. So option 2 is correct option.